Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about inference for a population mean. All right, so inference is when we're working with confidence levels and tests of significance. The definition is making conclusions about a population from statistics with a known degree of confidence. All right, so we will be estimating and testing a population mean. We always list the standard deviation with the mean. All right, so as a refresher, the formula for standard deviation is the square root of the summation of each individual x value minus the mean squared divided by n minus 1. We don't know the mean and we can't know the standard deviation. So we will be estimating with these two things, estimating the mean mu and the standard deviation sigma. And instead, we are going to use x bar and s, so the sample mean and the sample standard deviation. What is the sampling distribution for a sample mean? So remember, when we were working with sampling distributions, x bar is approximately normal with a mean of mu and a standard deviation of sigma divided by the square root of n. That was for the distribution of a sampling distribution. Because, again, we don't know mu and sigma, we're going to use x bar and s over the square root of n. So when we do this, we can't use z-scores, okay, because it's not going to be exactly a normal model, and we're going to use a t-distribution instead. So a t-distribution is also called the student t-model. This is a family of distributions, so there's more than one distribution. It is very similar to a normal model in that the center is at 0, it's unimodal, it's symmetric, and the curve never touches the axes. Okay, so if we had a degree of freedom of 5, it looks something like this. Degrees of freedom of 20, getting closer and closer to a normal distribution as the degrees of freedom increases. So the model changes based on the sample size and degrees of freedom. Degrees of freedom is your sample size minus 1 for this type of scenario with means. It's generally wider than the normal model, and the larger the sample size or degrees of freedom, the closer the student's t-model approaches the normal model. All right, so we're going to talk about doing a one sample t-interval. Our conditions are going to be the same pretty much, so randomization, 10% condition, and then our normal condition. Remember, normal, when we were working with means, there was 3 ways of checking that normal condition. Either it can be stated that it's coming from a normal population. We can look at a histogram of the sample values, and we want it to be approximately normal, no obvious curves or no obvious outliers. We can look at a normal probability plot, and we want the normal probability plot to be pretty straight, like form a straight line. And sample sizes can also be greater than 30, which kicks the central limit theorem in, right? So if that is true, we're going to say our conditions are met. We're using a t-distribution, and we're doing a one-sample t-test or t-interval. All right. In the do step for a one-sample t-interval, we're going to calculate or be given x bar, s, and n. So the sample mean, the sample mean, the sample standard deviation, and the sample size. We're going to find the degrees of freedom, which is n minus 1. We're going to find the critical value, t star. We're going to use inverse t, or we can use our tables that come along with our reference sheet and formulas. And then the formula for this interval is our statistic plus or minus our critical value times the standard deviation of our statistic. Remember, critical value times standard deviation of your statistics, that makes up your margin of error. So it's x bar plus or minus t star times s over the square root of 1 gives us our interval. Our conclusion, we would be saying we are blank % confident that the interval from blank to blank captures the true mean, whatever the context is, goes there. All right, in your calculator, you're going to put the data into list 1. You're going to press stat, test, you're going to do a t-interval. If you have the data in list 1, then use data. If you're given x bar and s, then you're going to choose stats. So when you go into t-interval, you're going to have 2 options, either data or stats. So if you have a list of data, you're picking data. If you have just the statistics, you're going to pick stats. And then this will give you the interval as well as x bar and s. All right, so we have an example. A coffee vending machine dispenses coffee into a paper cup. You are supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Below are the amounts measured in a random sample of 20 cups. Is there evidence that the machine is shortchanging customers? Construct a 95% confidence interval. All right, so this one I have a bunch of data. I have 20 data points. I'm going to start by putting those into my list 1. All right, so stat edit, enter all those data points into list 1. All right, state, I'm going to define my parameter. So my parameter is mu. I'm working with means, not proportions now. So mu is the true mean number of ounces of coffee dispensed by the machine. N was 20. Degrees of freedom is n minus 1, so 20 minus 1 would be 19. My confidence level is 95%. X bar, so the sample mean when I put all those data values in, is 9.845 ounces. The sample standard deviation is 0.1986 ounces. Remember that you can get that if you put all the data in. You can go to stat, calc, 1-bar stats, and you can get the mean and standard deviation. You can also get it when you do the one sample t interval in your calculator. All right, plan. This is where I'm going to check my conditions. So random, it said they took a random sample of 20 cups. The 10% condition, 20 is less than 1/10 of all cups of coffee dispensed by the machine. And normal, again, I can't use the central limit theorem because my sample size was only 20. They didn't say it was coming from a normal distribution. So I'm going to go ahead and make a normal probability plot since I have all the data in my calculator. To make a normal probability plot, I would go to second y equals, which is my stat plots. And I'm picking the graph type is like the very last one. It kind of looks like a ladder, sort of. And then your data is in list 1. And you'll get a plot that looks something like this. So since our normal probability plot is approximately linear, we can proceed. All right, I'm going to say conditions are met, and then I'm doing a 1 sample t interval. I'm taking my formula, it's my point estimate, plus or minus my margin of error. Okay, or statistic plus or minus critical value times the standard error of your statistic. My statistic is x bar, plus or minus my critical value is t star, times the standard error of my statistic is sx over the square root of n. X bar was 9.845. T star, I'm going to do inverse t. Okay, and then I'm going to go ahead and figure out that value. So we'll go over that quite a bit in class. But the area, you have to put the area in like to the left. So if it was 95%, that leaves you with 5%, which leaves you with 2.5% on the left tail. So 0.025 is your area, and then your degrees of freedom, and it'll give you t star. And sx is my sample standard deviation, and n, the square root of n, would be the square root of 20. Okay, and then when we put this into our calculator, we get this interval, or if we calculate that out, we get this interval, 9.752 to 9.938. So, conclude. We are 95% confident that the interval from 9.752 to 9.938 ounces captures the true mean number of ounces of coffee dispensed by the machine. All right, a 1 sample t-test. So for the state section, we need to define our parameter and then also include our null and alternative hypothesis. So our null hypothesis is always going to be mu equals whatever number, and the alternative will be mu is either less than, greater than, or not equal to that same number. All right, same conditions as our interval. If our conditions are met, we're going to use a t-distribution and do a 1 sample t-test. All right. And the do piece, we're going to calculate or be given x bar, the sample mean, s, the sample standard deviation, n, find the degrees of freedom. Our formula is going to be t, our test statistic, equals our statistic minus our parameter divided by the standard error of our statistic. So it's x bar minus mu over s over the square root of n. We're going to get our p-value, which is the probability that our test statistic is greater than or less than. And if it's a not equal to test, it's 2 times that probability. In our conclusion, we're going to compare our p-value to our alpha value. It's the same 2 sentences we've been using for proportions, except for we need to keep the context in terms of means. So We reject or fail to reject the null hypothesis because our p-value is less than or greater than our alpha value of whatever that is. We have sufficient or insufficient evidence that the true mean blank context is whatever. So try to restate it back with the question you're being asked. In your calculator, you're going to go to stat, test, and then you're going to pick an option for a t-test. Again, if you have data, you're going to choose the data option. If you have stats, you're going to choose the stats option, and you'll enter in the sample mean and the sample standard deviation. All right. The EPA wants to show that the mean carbon monoxide level of air pollution is higher than 4.9. Does a random sample of 50 readings with a sample mean of 5.1 and a sample standard deviation of 1.17 present sufficient evidence at the 0.05 level of significance to support the EPA's claim? Previous studies have indicated that such readings have an approximately normal distribution. All right, so state, we're going to define our parameter. Mu is the true mean carbon monoxide level of air pollution. My null hypothesis would be that mu is equal to 4.9. The alternative would be that mu is greater than 4.9. All right. X bar, my sample mean, they told me was 5.1. My sample standard deviation is 1.17. N is 50. Degrees of freedom is 1 less than 50. And my alpha value is 0.05. Plan. Random. It said that it was a random sample. And my 10% condition, my sample size was 50, is less than 1/10 of all possible air pollution readings. Normal. It said that the such readings have an approximately normal distribution. So the population distribution is approximately normal. That was stated. Okay. So all my conditions are met. I'm going to do a one sample t-test. So my standardized test statistic is equal to my statistic minus my parameter divided by the standard error of my statistic. My test statistic here is a t. This is a t-test. My statistic is x bar minus my parameter is mu over my standard deviation is s over the square root of n. So I have 5.1 minus 4.9 over 1.17 divided by the square root of 50. Okay, again, my calculator can really do most of this for me. So stat test, t-test, I get a t value of 1.2087 and a p-value of 0.1163. All right, I'm going to draw my t distribution. This is not a normal distribution, so this is a t distribution with 49 degrees of freedom. The mean is at 0. I'm going to my t score of 1.2087. It was a greater than test, so I'm shading above. My conclusion, we failed to reject the null hypothesis because our p-value of 0.1163 is greater than our alpha value of 0.05. We have insufficient evidence that the true average carbon monoxide level of air pollution is greater than 4.9 units. All right. Go Seahawks.